Good afternoon. My name's Peter Lawrey, and I'll be talking about Lambda puzzlers. I'm a developer and consultant for, I've worked with investment banks and hedge funds the last 10 years, and also a Java champion, and I've got the most answers for Java and the JVM on Stack Overflow. Also interesting to me is that I'm the only gold medal holder for memory and file I/O, so it gives you an idea of my sort of low-level bent, and that's in any language. I thought I would give a bit of a rundown of lambdas and streams, but more focusing on lambdas. What are they really? How do they operate? What are some of the gotchas, and how should they really be used? So I'm going to look at things like what are they good for? When's a good time to use them? How and why would you serialize them? How can they be interchanged with other kinds of objects? And last but not least, some of the performance considerations. So there's two ways of writing a lambda. One of them is as a method reference, and the other as a lambda expression. So one of the differences with a method reference is that you're naming a method, and that is significant when you come to things like serialization. But when you use just a normal lambda expression, then actually a method gets generated for you in that class. There's a static method that actually holds the implementation, and that may or may not change, particularly if you change the order of your code, for example. So what are lambdas? Well, they're actually classes that are generated at runtime. So they're not generated by the compiler. There's no .class file for you to see. But at runtime, you can do get class on a lambda, and it will give you back a somewhat not very meaningful string, but you do get an actual class back. And so what they can do, and in fact, the class name is deliberately obscure so that you don't find interesting uses for it and then complain when it breaks. You can't override the toString of a lambda, which has or the equals or hash code, which has the downside that you can't compare two lambdas and you can't get very useful debugging information off them. But apart from this, they're very useful for snippets of code. Now in terms of streams is an API that uses lambdas, but lambdas are not limited to streams. You can use lambdas in other APIs as well. And we have our own APIs, for example, that are open source. We use lambdas a lot, but we don't use streams very much. So they are actually separate in that sense. Also, with streams, you don't have to use lambdas. You can use, say, anonymous inner classes or other implementations. It's just that using lambdas and streams together is a fairly natural thing to do. So you've got imperative style coding, which has been around for quite some time. Up to Java 7 is your only option. So you have a loop quite often to iterate through some data set. Now with a functional style, you can construct a stream. And for the most part, it will do the same thing. It will have very simple performance properties, but often when you look at some trivial examples, and certainly my initial reaction to a lot of the easy examples to do with streams is that often when it's simple to understand, it's often difficult to see why you would even use streams in the first place. However, as you get into more complex examples, you will see that streams actually become, and lambdas become much more powerful, and they allow you to do things that in a loop would be quite painful. One of my earliest observations and revelations was things like group by. So collections.group by is very easy to do with a stream, but actually quite difficult to do with a loop, because you have to maintain, well, what was the previous value, what sort of collection am I using, and so on. So pure functions, well, there's a lot written there. Unfortunately, I've probably got too much material, but anyway. So we've got, what is a pure function? A pure function is one that has no side effects. And this is an important concept for for functional programming is that you want to minimize the amount of side effects involved. That way you can reason about what those functions do, and in particular, as we can see later, you can parallelize it, so you can run that code across many threads. There's no interaction between those threads because there's no side effects. So you want to use pure functions as much as possible, even before lambdas. I would have advocated, even in Java 7, you want to make your functions pure where you can. You want to minimize side effects. Or, perhaps as a rule, if it's going to have a side effect, you just have one side effect. If there's more than one side effect, is when you get situations where it really gets confusing. So here's a little puzzle for you. And this puzzle is, which ones of these methods are pure methods? That is, that they don't have side effects. Now, one of the big hints is that a pure function should always return the same result for a given input. And as you can see, actually, the first example is a pure function. The second one is definitely not a pure function. It changes state and it gives you a different result every time. Concurrent time millis might give you a different value each time, so it's not really pure either. Get user count might keep changing. And lastly, you're getting an empty tree map, and you might claim that that's pure, but from an object point of view, you're getting a different reference each time. So, in fact, that's not really pure either. So one of the things that you find in reality is that, well, people say, well, functional programmers come to Java. The way you will probably end up using it isn't really pure functional programming. You will have side effects, and you will use it in ways that, in a more pure functional language, would be avoided. So some classic examples of these are the consumers and runnable. These only exist to have side effects. They don't return any result. So as a result, they're clearly going to be, they either do nothing or they're going to be an impure function. So they're the ones to watch out for. So if you can refactor the code, and you'll see some examples later, where you can avoid using consumers or runnables, then that's likely to be an improvement. So this is a little puzzle for you. So in this case, I've got an executor service. Well, I've got two pieces of code that do the same executor service. And in the first case, I get an exception being thrown. But in the second case, no exception is thrown. And the only difference between the first and second cases is that I'm returning null. So in the second case, I return null. The first case, I don't. Anyone see why that might happen? Why it might be that in one case it's allowed to throw an exception, the other one is not? Yes?
It's because you have a difference between one is calling a runnable.
Yes.
And the other one is calling a
callable. So the first one is a runnable because it doesn't return anything. So this is part of the type inference magic. It says that it's not returning anything, it must be a runnable because that's the only type that's overloaded that doesn't return anything. In the second case, there's only one method that can return something, that's callable. One of the differences between runnable and callable is that callable can throw a checked exception. Runnable cannot. So you get this strange side effect that by returning null, I now no longer have to catch my O exception. So mixing imperative and functional code isn't ideal, and Java doesn't have any way of preventing this or even flagging it, but it's something that you should try and be aware of, because you will find things get a little bit more difficult if you start to mix these two forms. So there's a couple of examples here. This is based on some real examples. In the first case, validate was a method that threw an illegal state exception if that item was invalid. But obviously, for each, it's taking a consumer. It only exists for a side effect. And that side effect is that it will throw an exception if any one of the elements is invalid. So this is not really functional programming, but even though it's using the functional libraries. It works. Maybe writing it another way would just be not necessarily an improvement, but it's something you should be aware of, that this exists for a side effect. So in the second example, you can decide to remove, based on the filter, all of a particular element. So this can have some strange effects, particularly in parallel, because you're altering a list you're iterating over. So it's generally not a good idea. So one way that you can refactor this, so in the first example I have a mixed style because I'm using the functional interfaces, but then I'm calling put, I'm using a consumer. Instead of doing that, I can collect all the results of the map into a new map, and I'm only returning a result. So there's no consumption going on, and you're producing a particular result. You're not altering anything. So that's one of the key aspects. Is you shouldn't really be altering anything in any of the lambdas in a stream. So there's an example of where this goes particularly badly, is if you call computive absent inside a computive absent. Right? I actually accidentally did this, although it wasn't as obvious as that. It was more complicated, and in this case I've picked a key which is an enum, just so that I can show you what enum map does. Now the behavior here is undefined because this is not intended. You've got a side effect inside Lambda which will be executed when the value is absent. So what happens with different maps? Well, it depends on the map. In many cases, you don't get the first value, you get the second. You get hello equals 2. In some cases, like hash table, you get both keys. So you get a duplicate key, which is not particularly good. Linked hash map, you get a duplicate key again, except in the opposite order when you two-string it. Concurrent skip list map is the only one which does what I think it should do. And in fact, as a short-term workaround for that code, I started using concurrent skip list, later decided to just refactor the code so it didn't do that in the first place. Probably the worst one is concurrent hash map, and that's because the locking that concurrent hash map uses internally is non-reentrant. So it deadlocks itself or live locks itself. So that's not ideal. So in lambdas you have what's called capturing and non-capturing. A capturing lambda is one that takes values from its context, and a non-capturing one is one that doesn't. It retrieves any values it needs when it runs, or it is passed every value that it needs. So this has some side effects. So in the first method, the value that's returned is non-capturing. The lambda that's returned is non-capturing, which means that you always get back the same object every time. So the JVM will treat non-capturing lambdas as something that it only constructs once. So it constructs it once when that line is run, and then that gets cached for the rest of the life of the program, or until perhaps that class is unloaded. Now in the second one, I'm using a method reference. But this method reference is capturing. It takes a copy of what system.out is, which also means that every time I run this, I get a new object. So it captures it again and again. And in fact, you can change system.out, so it is meaningful to do this. So if I create this consumer and then alter system.out to be some other output, this will continue to write to the old system.out because it's taken a copy. And in the last case, we've got something similar. We're taking an argument and returning a value. It's acting as a consumer instead of a runnable. And again, this is non-capturing. All the values that it needs are being passed in rather than retained. So this has some side effects, as I mentioned. So in the first case, it's non-capturing. So if I call this method twice, I get the same object. If I call it twice for the second case, which is capturing, I get different objects. So if I put these into a set, in the first case I put them into a set, I have a set of 1, and in the second case I have a set of 2. If I try and remove the element from the first one, it may well work. I can add it to a set and then remove it later. However, in the second case, I have to be a lot more careful, because if I try and remove it, it will remove a new object which doesn't exist. So nothing actually happens. So it compiles, it runs, it just doesn't actually alter the set. So it's I've run into that situation with subscribers. So another puzzle for you. Do we need to close this? So most streams don't need to be closed. It's a closable. A base stream is a closable, and you can call close on it. But in most cases, the only thing it does is it prevents that stream being used again. So if you try and use it after it's been closed, it'll throw an exception. But in this case, you actually do need to close it, because it creates a file resource. And for whatever reason, when you reach the end, when you get to the end for each, or an exception is thrown, it doesn't close off that resource. You have to manually do try with resource on a stream to ensure that that resource gets cleaned up. Again, this is a subtle bug, because most of the time this is fine. It will eventually get cleaned up when it gets GC'd, and that will close off the file. But if you create these faster than the GC cleans them up, then you can run out of file handles. So it's a fairly subtle bug that doesn't show up in some simple unit tests, for example. So you have to know that some streams that use particularly file resources are likely to have to be explicitly closed off. Serialization. So one of the benefits of Lambdas compared to anonymous inner classes is they capture less scope. This makes serialization easier because you're capturing less data, which might not itself be serializable. So you have to be careful what gets captured as to whether that's appropriate for serialization or not. Now, there was some discussion when this feature was added to Lambdas, that you could serialize them. And in particular, some people, Brian Gertz included, was thinking, well, this is probably a feature we don't really want to be supporting, but there was enough people who convinced him otherwise. So it does mean that what you can do serializable, it's something that's not there by default. So you have to jump through a few hoops. So one of the hoops that you have to jump through is quite scary. It's having, you have to cast, but it's a cast that has, this is a compile time cast, not a runtime cast. At compile time, this cast says, this is the type of Lambda I need to produce, and it changes the bytecode appropriately. It's also odd that you've got a cast here with an AND in it, so you've got multiple types. In fact, you can add as many marker interfaces as you like using this style of casting. However, the whole point of Lambdas is to avoid boilerplate, and as you can see, the cast is longer than the method or the piece of code that I'm trying to wrap. So this style isn't particularly friendly. So how can you get around this? Well, one way of getting around this is to have an API that uses an interface that is serializable. So when you define your Lambda function, you say that it extends serializable at the time you write the API, and then people using the API don't need to know this detail. That hides that detail away from them. So again, we've got three methods. In the first case, as I mentioned before, this is capturing. So when we come to serialize it, it blows up because it says that system.out's a print stream and it's not serializable. We can't serialize it. Second case, it will actually serialize, and you can send that across the wire and execute it on the server, for example. What will happen, though, is it'll just print out a line on the server, won't print out the line on the client. And the last case is where this is where Lambdas have something above our benefit over anonymous inner classes, is apart from it being more verbose, the anonymous inner class will capture the this of the context. So if it's not static, it captures the this, even if you don't use it. And that creates not only an overhead, but it actually makes it non-serializable, which is probably a good thing, because if it is serializable, it'll be sent across the wire, even though you're not going to use it for anything. which is something of a waste. So why would you serialize a Lambda? Well, there is a number of distributed APIs out there. We've got one, Hazelcast is another one I know that use this technique, where you can write snippets of code on a client, and then they are executed remotely on a server. So it can take that piece of code, pass it to the server, and the server then executes that code. It can do it atomically, and then send the results back to the client again. It's not like it has to take some sort of global lock, send the data to the client, apply the result, and then send it back again and then release a lock. Fortunately, it can be all done where the data actually resides. So this can lead to some more complex examples where this is based on Redis. You want to, say you've got a collection, a map, and you want to get all the keys that match a particular pattern. Well, if you were doing this, executing this on the client, it would have to download every key, then it would match them against the pattern, and then you would get your result. But in this case, we can write a snippet of code that, because it's serialized, it gets sent to the server executes this, and it only sends back the keys that actually matched. The nice benefit of this is that you have all in one place, both the code on the client and the code on the server, all nicely self-contained. So it makes it much easier to read and understand what it's doing. Also, if the client, for whatever reason, say this is actually being executed on the server, then the server can just say, well, I'm not going to serialize it. I'll just run it myself. So this can all be handled in the library without the developer writing this interface needing to know those details. So say we want to turn a list into a map. So this is actually quite a common use case of streams. And one of the functions that can be used is a thing called function identity, and it has a very simple implementation. I actually favor just listing t arrow t, because in fact it's shorter than the method, writing the method call itself of function.identity. And then you can also see what it does a little bit clearer. But so that's converting from one data type to another is a fairly common use case where streams do a very good job. So another puzzle for you. I create a stream of 6 integers. I print out all the even integers, and then I want to print out all the odd integers. Does anyone know what happens when I do that? It'll fail. And in fact, what happens is that it gets an illegal state exception on the second attempt, telling you that it's already been operated or closed. So this is one of the gotchas of streams compared to some other languages where this is not the case. You cannot reuse a stream. So if you have a data set that you want to reuse, you might have to use a different library that does support this, or you have to take it into a collection, which you can then reuse as many times as you like. So I gave an example earlier of being able to sum up decimals, either imperative style or functional style. But what about big decimal? Because one of the things about big decimal, for me at least, is that there's, unlike say C#, there's no language support for decimals. It's just a library. And in fact, again, it doesn't have great support in streams either. So what you have to do is you have to do a reducing function. So you start with the value 0, it's a big decimal. Then you write a function that will take each value of input, in this case it was a series of trades, and then adds those values together, and then eventually you've got an accumulator. Now I've written it this way because it's the slightly more elegant way isn't as quite as obvious, but in the middle stage you're grouping together everything that thread will have. So if you parallel stream, so imagine you've got 16 threads, then every one of those 16 threads will start with 0 and keep accumulating those results. But finally, you're going to end up with one result for each of those 16 threads. How do I combine the results of those 16 threads? Well, that's what the last expression does, which is called add, and that just adds big decimals together. Now, a clearer way of rewriting this is actually to use map to extract out the big decimals we're interested in, and then you can see that all we have to do is, well, it's big decimal to add all the values within a thread, and then big decimal to add the values between threads. It's not quite as obvious because now those two terms are actually the same. So this is something of an anti-puzzle that comes up on Stack Overflow a lot. There's often the question, how many objects does this create? And often it's a little bit misguided. It'll have, say, a section of code that's got some strings, and really they're only thinking about, well, how many strings did I create, and do you understand how string literals work? But in fact, the reality is that most strings wrap a string char array. In Java 9, they'll probably wrap a byte array. And so that's actually another object. For every string, there's actually two objects. But it's worse than that, because in some examples, they don't just give you a snippet of code, they actually show you the main and the class it's in. The reality is, to start up main and to start up that class takes more objects, probably a lot more than you might have imagined. So this is particularly the case of streams, because as I mentioned, lambdas are generated at runtime. And there's a runtime library that goes and generates a bytecode and compiles it. So that on the startup, that can be quite expensive. Once the JVM's warmed up, it can be very fast. But to start with, on the very first invocation, certainly for the very first invocation of streams, it can be surprisingly expensive. So anyone hazard a guess as to how many objects this piece of code will create? Note, I put in system in.read, so the program just stops so that I can do a JMap and get a histogram of how many objects get created. Is anyone willing to guess how many objects get created? Well, actually, the closest estimate is 20,000. So from this one line of code, which has one lambda in it, and one array of 4 objects, we actually end up with 20,000, even though I used intstream, which is primitive. So this is what the dump looks like. You get integer arrays, which are really big. They're often used for character encoding. Char arrays, which are sitting underneath a whole lot of strings. Byte arrays, which are used for decoding classes. Then the next biggest one is actually to do with the code generation. It uses its own internal use of object web, which it uses to generate code on the fly. Finally, we get in string, and string has got 4,500. So if you're wondering about that string example I mentioned earlier, even without streams, just a simple hello world program, you're going to be looking at about 10,000 objects. So, and then it goes further down the class. The one at the bottom is my pet hate, which is string buffer. String buffer has been practically deprecated for 10 years now. Its Java doc says don't use it, use string builder, and yet the launcher uses it almost as much as it uses string builder. And the irony is that classes such as simple date format used string buffer, and yet simple date format is not thread safe. So how could this be? Well, there's a kind of design flaw. So if you've got something like hash table, you can do a get or an put, and they're useful operations in and of themselves. They're atomic. You can do a get and then a put, and that's all you need to do. It's a single operation. Whereas string buffer, each individual method is thread safe, but not a combination of them. So if you do append, that's it. You can't do a toString or another append, because that combination, it will release the lock in the meantime. So unless you've used external locking, string buffer is almost useless for multi-threading. In which case you may as well have used string builder and make it really clear that you're doing external locking. So yeah, there's a pet hate of mine. Never made any sense in my opinion. So how do lambdas perform? Well, we actually use lambdas in some of our low-level performance-based APIs. In this case, we're using lambdas in a couple of different ways. One is as a setter, and you'll notice that in the bottom part of the code, we're actually passing in an extra value as an argument to avoid creating a capturing lambda. So we create a non-capturing lambda on the right, and then we pass in that extra argument, which is in this case this, so that we can set that field on this. In the first case, its message field gets set. When the message field comes in, it's red. So with a bit of rearranging of the API, you can make it that your lambdas can be non-capturing by making that the additional data they probably need is an extra argument. So there's a little bit of refactoring, but it has the benefit that this can produce no garbage. So one of the interesting things about enums and lambdas is they can actually be used in some cases interchangeably. And in fact, we do in this API. So a lambda is an interface which has one abstract method. However, enums can also implement interfaces. So instead of having snippets of unnamed anonymous code, you can actually pass in an enum to where you would normally pass in a lambda, and now you've named it. This has some upsides, as I'll mention in a moment. But in this case, this is somewhat of a contrived use case because wire key, its only anonymous method is name, and it returns a string. But enum actually implements name for free. So in this case, we've got an interface which is a functional interface, but we didn't actually have to write any methods for it because enum gives it to us for us. So then we can, as you can see in this case, on the left-hand side of the code, here we've used lambdas, which allows us to create some arbitrary string names, or here we've used enums, and that way we can keep them similar. Now, why bother doing that at all? Well, actually, we can extend those enums and use them in other ways. So say I want numbered fields instead of named fields. In the enum, I can define those as an additional parameter of the wire key. So I can actually use other extensions and still use the same interface. So when should you use enums? Well, enums are a lot easier to debug because they're named. You can see them in the debugger by name. You can see their class name. You can then work out what they do fairly easily. They're much more efficient to serialize because all they serialize is the class name and the name of the enum. They can be easier to manage in a distributed environment because you can build a preset list of functions. So you can have one enum like operations, or in this case we've got map function. And then we can list as a whole series of enums all the different operations you can perform on a map. So we can decide in advance what operations you want to allow. However, lambdas are much simpler to write. There's less preparation involved. They integrate with generics much better because they can take into account the context of when they're used. So the same snippet of code can refer to different types and different situations. Whereas in enum, that's not the case. And they can capture values, which is another thing that enums can't do. So I've kind of given away the answer to this question, but what does the line at the bottom do? Well, the line at the bottom is a lambda that returns something that produces another lambda. And so this is kind of confusing. So, and this does happen, particularly around type inference, where you've got type inference involved. Where you've made your mistake and where the compiler gets confused and produces an error message can be quite different, because you can have many lines of code that are all working together. So how do you resolve this? Well, one of the techniques that I use to resolve this is I'll use the IDE to revert it or convert it to an anonymous inner class. And by using an anonymous inner class, in this case one inside another, I can see precisely what it's doing. And if the types aren't working out, I can make the types what they should be, and then use the IDE to switch back again, switch it back into a lambda, and now it'll all compile. So it's a useful trick when you're dealing with really confusing error messages to do with lambdas. Escape analysis. Escape analysis is actually one of the key optimizations in Java 8, for me anyway, because it can reduce the amount of objects being created. It can put objects onto the stack, unpack them basically. And it also can reduce synchronized. It can take away synchronized locking. So essentially what it does is that it works out whether an object ever escapes a method. And if it doesn't escape a method, it can apply optimizations that it couldn't do otherwise, such as not actually using the heap. So one of the key things that escape analysis needs to function is inlining, because if it never escaped the current method, that would be quite useless. You couldn't really do anything with it. But after inlining, all the code may be in that method now. So with inlining, you now get this big long Uben method. Then it can work out, well, does it escape after I've inlined everything? So how your inlining works is key to whether escape analysis is likely to function. However, they can actually get in each other's way. So this is just a note that you don't always, even with escape analysis, when it is working, you don't get as optimal code, but you get pretty close. And it's kind of for free in a way, because you don't necessarily even need to know it's there. This is why using a profiler, it could be very helpful, because you might read the code and say, oh, this is producing lots of objects. But if they're very short-lived objects and they only exist in one method, it might not be producing any objects at all, because escape analysis can kick in, put it onto the stack, and now no objects at all have been created. So one of the catches with inlining and escape analysis is that the thresholds are not, in my opinion, compatible. So the threshold, the limit of how big the method can be after inlining, when escape analysis stops functioning, by default is 150 bytes. But the limit at which it will stop inlining is 325 bytes. So I've actually had examples where you write a very simple piece of code and it's running and it's creating garbage, but then escape analysis kicks in, and then it no longer creates any garbage for a short period of time. But then it does a bit more inlinings, because it can. And now that it goes over the escape analysis threshold, and suddenly it's producing garbage again, because it's turned off escape analysis. So for this reason, I always suggest, if you're going to use escape analysis, set it to a higher level than your frequent inline size, and then you won't run into that situation. In this case, I'm using 3 times the default, and for me, it's never caused a problem. But your mileage may vary. So time for another puzzle. Does anyone know what this will print out? Yes, it's a bit of a mystery, really, yes. Well, here's a hint for you. There is no char stream or character stream. So in fact, chars actually returns an int stream. So when you print it out, it looks like this, which isn't very useful. Okay, so I know how to fix this. I will cast all the integers to chars. So let me give this a go. How did that go? Well, unfortunately, I did the same thing. And the reason is that what map does is it always returns the same type as what you started with. So in this case, I'm casting it to a char, and then it will take that result and cast it back into an integer again for you. Still doesn't quite work. So what we need to do is to turn them into objects. So again, I'm casting it, but this time it'll become a character object, which is not very efficient, but at least it will work and do what I expected. So I mentioned this example before. I won't go over it again. Okay, so group by, this is again from some real code. First we're filtering, and then we're using group by to group all the possessions for a particular symbol. So this is a reasonably common pattern for certain kinds of code. In our case, it was quite common. And like I said, trying to do this imperative style is quite hairy and messy. So this is where the first time I saw that lambdas and streams could be a real win in terms of reducing the complexity of code. Again, this is a real example to do with using toMap to create a new map, but applying a filter first. So you can use contains in a list or a string, but in this case it's useful because you can not only say contains, but you can contain something that matches a predicate or for which an expression is true. So that becomes a lot more powerful in terms of being able to match. This will inherently stop, and if you've used parallel stream, it will actually stop the whole lot as soon as there's one result that's successful. So it can cut down the amount of work even in parallel stream. It'll try and stop early. It can be used for something like a deep copy, where you go through and clone every entry. So you can do a copy of a list of positions in this case. Okay, so this one is coming into something of an anti-pattern. Again, this was from some real code. We were working on a project a couple of years ago, and it's sort of, well, let's collect the results and then do a for each on the results. Well, actually, it didn't need to do most of those things, and you can actually just map them and then collect the results to a list. So this is an example of sort of sorted. So one of the things about grouping by is that it uses hash map by default. So yes, you can sort the values, but the problem is that it then puts them into a hash map, and you may not, you're very unlikely to actually get a sorted result. So how do we deal with that? Well, grouping by allows you to specify a supplier for a map. In this case, a tree map, and that way I can construct the map in a sorted manner, all in one step, and then the map I return will be a sorted map. Now, in the previous case, I could have used a constructor for a linked hash map, but that wouldn't have been sorted. It would still, that would only continue to do insertion order. Another way of sorting is to actually chain them like this, where you have sorted by one thing, sorted by another, and sorted by something else. We found that that's actually pretty inefficient, because it's going over the data n log n 3 times, and we get much better results if we create one comparator that compares all of the fields. Now, interestingly, if you switch from this form to this form, you actually have to invert the order of the fields that you're comparing. Because in this case, the last one is the most important. In this case, the first one is the most important. So this is a rather ugly, somewhat contrived piece of code. You probably wouldn't want to write this all as one-liner. But what it is doing is it's actually taking the top 20 most popular words in a file, the most frequent. So it starts off by listing all the lines. Then it's doing them all in parallel. Then it goes through each of those lines and breaks it up into a stream of words. So /b is, separates on any white space. Then it collects them all by key. So the key is retained. So for every word, I now know I'll have a key of those words. But then the accumulator is not a list of the words, but it's actually just the counted result. So I end up with a map, which is a frequency count. But it's not sorted. So I can then take that entry set as a stream, and then I can sort them. Now, interestingly enough, type inference will only go down one level. It won't go into a nested method call like this line has. So even though 2 lines down, I didn't need to specify the types. In this example, on this line, I had to, where it's doing sorted comparing. So sorted comparing, I've had to specify, and this is how you do specify it, when it can't work out what type, in this case, the map entry is. So I'm now sorting it by value, reversed. So I've now got all the ones with the highest frequency counts first. I limit 20, so I just take the top 20. If there's any duplicates, I will just arbitrarily chop off some of the duplicates. And then I get all the keys. So now I have the top 20 words, and I can turn them all into a list. Now, trying to do that in imperative code would be tricky, but it also certainly couldn't do it as a sort of notionally one-liner. Now, streams aren't all good. I've seen examples such as these where people had decided they're going to use streams, and it would have just been a lot simpler if they hadn't. So in this case, I'm not too sure why they took a copy of the balances before adding them to the combined list. They could have just used add all. In the second case, again, you could have just used a couple of add-alls or perhaps a flat map. So you could do a flat map of the 2 lots of trades and then combine them into a list. Another thing we see, particularly people that aren't used to using optional, is that there's a sort of an attempt to avoid using optional. And I call that optional denial. So in this case, the easiest way to avoid using optional is you just do or else null. And then, of course, you have to go and check whether you got null or not. So you go back to your old programming style and pretend you're not using optional. This is, again, a real case where we not only check that the optional is not null, we also check whether the optional itself is null. And so this becomes a lot simpler. I probably should have included the example, but this becomes a lot simpler when you actually just use a series of streams, because you can stream off optional as well. Okay, so it's getting late, so I'm glad I finished a little bit early. So there's a little puzzler at the end, just at the bottom there. On my machine, when I run that, I get an exit code of 84. No, of 80. Because it divides up the work, and if the fork join pool hasn't started, what will happen is the work assigned to the current thread comes in first, and that just happens to be on my machine for the number of CPUs I have. It starts at 80, and then I get a system exit of 80, and all the others get thrown away because they get killed off. Anyway, thank you. Do we have some questions? No? Oh, okay. You can ask me questions later if you like.